We introduced families of point transformations because that was the best way we could describe symmetries. Now, symmetries are just what they sound like. If you have a system and you make some change, so we might transform it in some way, then under this transformation, the Lagrangian doesn't change. So we usually work with situations where when the parameter is 0, then the transformation is just the identity. So s equals 0, when the parameters are 0, we're making no change, but then as we make those parameters non-zero, we might be making some change, and whatever change we make does not change the Lagrangian. And this is called a time-independent continuous symmetry. And the time-independent is clear, it means this works for all time, and a continuous symmetry means that we've got this smooth parameter that we can change in a continuous way, and that doesn't change the Lagrangian. An example of a discrete symmetry might be perhaps you could flip the sign of a coordinate and that wouldn't change things. But that only has two values, 1 or -1, whereas this thing is like a translation. It's a continuous parameter that we can change, and under that transformation, the Lagrangian is not changing. That's a time-independent continuous symmetry. Wow! Aren't you Emmy Noether, the influential German mathematician known for your groundbreaking contributions to algebra and theoretical physics? Well, that probably explains why you're discussing the fundamental connection between symmetry and conservation laws then. Well, there you go. So Emmy Noether was doing her work about 90 years ago, which explains why she uses old-fashioned terms like integral of the motion instead of conserved quantity. But what she discovered, essentially, was that this time-independent continuous symmetry of the Lagrangian meant that there was definitely a conserved quantity. So if you can find a symmetry of your system, you can find conservation laws. We can make this constructive straight out of this equation here. So if we see that the Lagrangian is not depending on s, then we know that the derivative of the Lagrangian with respect to s is 0. And we can expand that out using the total derivative. Look at this first term, and we know what that is from the Euler-Lagrange equation. And a little bit of insight, we look at this and we can see that this is the total derivative of something from the product rule. And there we go. What we have is we have the fact that we have a time-independent continuous symmetry tells us that this quantity here is conserved, i.e. it's constant in time.